Hello, it's Tuesday, November 26th, and this video is about Chapter 15. You'll recall that at least since through Chapter 12 or 11, 12 really was formally when it was introduced, we're in bivariate association. We backed up a little bit into Chapter 11 to do crosstabs, backed up a little bit farther to Chapter 10 to analysis of variance. But it's bivariate relationships either way. And today we want to talk about three aspects of that are inside Chapter 15, scatterplots, correlations, and regression analysis. And we'll walk through those individually here in a minute. But recall the matrix that I put up here on the board before, I think in the last set of videos, where we talked about the dependent variable equals the independent variable. We don't need to go back through that part of it again. But we had crosstabs. Chapters 11 through 14, categorical variable was dependent, categorical was independent. Analysis of variance, the dependent variable is continuous and the independent variable is categorical. And then what we're doing today is correlation, where both the y variable and the x variable are continuous variables. So, and you'll see from Chapter 15, association between variables measured at the interval ratio level. And we talk about association, much like we have been talking about association from Chapter 12. And you'll see in here, in a second or so, page 363 of the book, Chapter 15, that we're back at looking at whether there's an association, what is the strength of the association, and what is the direction of the association. And we'll talk about those three things in particular, introduce them in the context of the scatter plot. Okay. So, and then, in a way, what we're ending here is with regression, which I've written here as prediction. You'll see on the third or fourth page in the chapter, they talk about regression and prediction. So this kind of concludes the semester. In fact, this is the last chapter. Concludes the semester of social statistics, our discussion, this video today. Although I'll do a video, kind of a warm-up video for the final exam, and how all that'll be next week. But we began with descriptive statistics, chapters 1, 2, 3, and 4, rates and ratios, central tendency, dispersion. We went to inferential statistics, more specifically, when we were doing one sample case and two sample cases, where we were testing what we had in our sample against what was in the parameter, or what we thought was in the parameter, and that includes confidence intervals. And then as we moved into chapters 10 through this chapter, we're in bivariate, explanatory statistics, and that is what we're trying to figure out here. And you'll remember the lambda and the gamma for the crosstab. Here we're trying to determine how much of the variation in y is explained by x. If there's income, how much of the variation in income across a population is explained by the variation of education across the population. So we're in explanatory statistics, and now towards the other piece of this, the third piece in this chapter, we're in predictive statistics. So from explanatory to predictive, all in the larger umbrella of inferential, because what we've been talking about all semester, all the sampling, all of the calculations that we've done have been based on a sample that's been drawn down from the population in adequate numbers, random enough to make it representative, and then we use the finding of that sample, which is our statistic, to estimate what we would have found in the population parameter had we gone directly from the population to the parameter, which we've already decided would be too expensive both in time and personnel and money and all of that. That, in a nutshell, is what we've been up to all semester. All right, let's look at the scatter plot. Now, when we're doing things like this, I've sent you demos, and in the in-class version, we've gone over the demos, but I've sent you the online class, 3 demos a little while ago. One on the same subject, where the same dependent and the same independent variable, we look at that relationship between the two variables expressed as a scatter plot, as a correlation, and then as a regression and predictive. So when we are doing this, then these are, and one of the reasons why they're in the same chapter, I suppose, is that they're logical progressions. First, you do the visualization of the relationship between two variables as it's spread across a scatter plot, and then you look at what is the coefficient of determination. You get the correlation, the R, and you square that, and that tells you how much of the Y is explained by the X. And then when we come over here to predictive statistic, we move beyond explaining, and then we want to say, for every change in X, how much change do we get in Y? In other words, if we were talking about income and education, for each year of education, how much on average do you get in terms of increase in income? So we do predictive. They've got a really good illustration of all three of these in the chapter, where they're looking at to what extent does a husband do household tasks. And the theory is there, the hypothesis is, the larger the family, the more children there are in the family, the more hours of household tasks does the husband. And you see that expressed throughout the first part, or throughout the chapter, both as a scatter plot, and then a correlation, and then as a predictive. Okay, so let's, I've got a cup of coffee here. It's cold in my office. I don't have a heater. It's 40 degrees outside, so I'm going to be drinking some hot coffee while we do this. It's a Starbucks coffee, and it gives me, whew, it also tastes good, and it's hot. All right, scatter plot. Now, you can see, you don't need to worry about what you can see on my crazy whiteboard here, but referring you to page 362, you can see the scatter plot that they did. And basically, what the scatter plot is, you've got, let's say it's a person who's A, is person A, and let's say this is 1, 2, 3, 4, 5, and this is 1, 2, 3, 4, 5. X here might be children, and Y here might be hours worked. And so person A, let's say, has 4 children and works 3 hours. So here comes, so they're about right here, and we draw that line and that's person A. At the intersection of how many children they have and how many hours they work. This is basically off a survey, right? How many children do you have? I have 4. And how many hours of household tasks do you do? Well, about 3 hours a week. So that's their response to the survey, and then we plot it out. And you can see there that we've got, this thing tends to run like this. So it's a positive relationship. And I say that because if we were to draw the line that you're asked to do, it would be like that. You try and find the line that sort of splits the difference between all of this distribution, this scatter. And if the line moves to the upper right-hand corner, it's a positive relationship. If it moves to the lower right-hand corner, going down, then it's a negative relationship. In other words, as X goes up, Y goes down. In this case, as X goes up, Y goes up. And you draw the line through the scatter, known as a scatter plot. So this is the visualization of the relationship of Y equals X, in this case children, and the relationship at father's household tasks. So we plot it out. We get a visualization of it. We can see that it is a positive relationship because it's going up. And we can see that it's fairly steep. If you look on that diagram on that page, it's steep. So that would suggest a strong relationship as opposed to one where the slope, this is the slope, an important concept for what we're going to be doing as we move through this little video, then you can see the slope is relatively steep, suggesting a strong relationship between numbers of children and household hours. If it's down a little bit like this, then that's moderate. And of course, if it's like this, it's negative. Now, if it's horizontal, flat, that means it's independent. Neither one nor the other relate. They're not related. They're independent of one another. But here, as you can see there, we've got a vertical, not a vertical, but a positive slope. And so there we have a visualization of a relationship that's reasonably strong. There is a relationship, it's reasonably strong, and it's positive. So there you got a visualization of something that's important in terms of your scatter plot. Now, if you go on over here a little ways, I don't have these things marked, but if you go on over to page 370, you have the correlation. which is the Pearson R. The Pearson R gives a mathematical value to the relationship that we have sort of drawn here on the scatter plot. It gives you the mathematical value. And then if you look at how they've done this over here, you can see that following that same story, that if you go down on the bottom of page 371, you see R equals 0.50. Now, that's interesting because the R varies from -1 to 0 to +1. The closer that the R is to a 1, the stronger it is. So whether it's a -1 or a +1, the closer to the 1, the stronger it is. Well, 0.50 is sort of halfway between 0 and 1, so we'd have to call that probably moderate, maybe. Something that's 0.6 or 0.7 would be a stronger value. But, there it is. And that's the R. Then we have what we call the coefficient of determination, and if you flip the page to page 372, you'll see what that is. And that's simply the R squared. So if we take, in this case, 0.50 and square it, we get 0.25, if I did my math correctly. 0.25. Now, just like we did for the lambda and the gamma, we multiply that times 100, and we get 25%. And so then we can say, from the coefficient of determination, the R squared, about 25% of the amount of hours, or the variation in hours that a husband works, is explained by number of children. 25%. Now, you say, well, what happened to the other 75%? Well, we don't know. That is going to be something that we'll talk about here, which is a residual. In other words, what's left over. Our model has explained 25%, and we only modeled the variation in father's household tasks by children. But there could be other things. Age of father, nature of employment, could be a number of things. But we chose to model this with just one variable, and that being the numbers of children. Now we use the word model, and you'll see that comes into the forefront here, because if we were to do this is the regression equation that you'll see. The formula is on. Hold on here while I flip around on the pages. Well, I don't know. It's in here somewhere. Oh, formula 15.1 on page 356. 66. If we were to, this is just a single x1, but we could do y equals alpha plus beta times x1 plus beta times x2, etc. In other words, we might put father's age in here as well as number of children, or some other thing that might be of interest to us. So when we use the word model, we realize that there are scores or more of variables on the right-hand side of the equation that might explain, to some extent anyway, the number of hours on average that a husband works. But there could be many of them. But we're modeling this relationship by looking at only children at this point. Truth is, there are probably a lot of X's that would influence, a lot of things out there that might influence. And one of the things we do in statistics is we do a whole bunch of bivariate relationships, whether they're categorical or ANOVAs or whatever they are, and look at each individual variable in relation to the Y and determine which of the ones are the stronger in terms of influencing the Y, and those are the ones we put in our regression model. So there's a winnowing out of the weaker relationships to retain in the stronger relationships. So we'll assume that we've done that, and we want to focus on the children here, numbers of children. Okay, so we've seen how it is seen, the visualizing of it, the slope, the degree of slope for the strength, that there is a slope means there's a relationship, and whether the slope is up or down is the direction of the relationship. If it's down, it's an inverse or negative relationship. We've done a correlation on this, And then we found that, and then we squared it to get the coefficient determination and discovered that 25% of the variation in household tasks done by fathers is explained by numbers of children. All right. So then what we want to do is we want to do the regression. We want to predict. Now, what we did with the correlation, we explained the numbers of hours. But what we want to do now, based on children, but what we want to do now is predict for each increment of children, how much additional hours would a father work? Not that they sit around, parents, and say, well, if we have 3 children, then you're going to be working on average this number of hours. This is family research where we're just kind of looking at what on average happens out in families, not that anybody makes a decision. A husband and wife sit down and run a regression model to determine what's going to happen in the household. Probably only weirdo statisticians that are married to one another might do that. But anyway, so here then, we were able to turn into a prediction, kind of a, like if we're doing research or practice of some sort, then we would use a model like this to be able to predict it. Now there are plenty of different kind of illustrations, like you'll see in the homework I sent you, and then your demonstration, that where as poverty goes up, crime rate goes up, relationships predicting crime based on poverty, are predicting numbers of children based on education of parents. A number of ways that you can do these things. Like in my research, I predict, my colleagues and I predict what level of autism will we have given a certain level of ambient mercury in the air. If it goes up this much, how much more autism would we expect? So there are a lot of ways that predictive regression can be used. This is just an illustration. So I'm not asking you anything about the formulas, but you can see them on 367, 368, and in there. So if we look at the bottom of page 369, you'll see where they have taken this formula and plugged in the intercept and the slope. Y equals the intercept plus the slope, times x. And you can see as you go back over the previous 2 pages how they derive the 1.49, y equals 1.49 plus 0.69. And what they put in that for x is 6 children. So this is predicting how many hours would a husband work on average if the family had 6 children. And then when you look at that regression model, predicting model there at 369, you can see it predicts that a husband would work about a little over 5.5 hours a week. And then you can put 3 children in place of 6 and do the math. Or you could do 12 children in place of 6 and do the math. And so there you can see how you can predict. Given 9 children, what? Giving 12 children, what? Like in the community, one of the things that we do, if poverty can be in your control, although not so easy from a population standpoint in the community, but you can say to the mayor, if we could lower where you got y as crime and x equals poverty, if you could, they're inversely, they're positive related. As poverty goes up, crime goes up. So if we were to say to the mayor, if we could get poverty down to 20%, then we'd have this crime rate. Right now we're at 35 and we have this crime rate. But if we were to somehow get to 60, which we don't want to get, we'd have that much more crime rate. So there's criminal justice applications. There are numerous kinds of applications, and scatterplots and correlation and prediction, and you'll see that in the demos, the demo documents that I sent you. All right, let's take a few minutes and look at the demos. The first one, what we've got here, is the scatter plot is Florida county crime rate by county median income. The dependent variable is Florida county crime rate. That's what's varying, the Y. And the independent variable is median household income. How much does income influence, or is there a relationship between income and crime? And the null hypothesis, we don't have to go through that. You know what that one is. So then you freehand draw this, and if you look at the scatter here, you can see that the line goes up to the upper right-hand corner. So that would suggest that as income increases, crime goes up. So you'll get a line going like this. It looks pretty steep, like a pretty steep slope. So there you can see that there is a relationship. It's positive because it goes like that. And the line that you would draw, probably would be. Let me draw a line here. This is just approximate. Looks pretty strong. Looks like a strong line as opposed to one more closer to horizontal. And that's what you do with the scatter plot. It's an early diagnosis of the relationship, one that you can visualize. You can see it. Now, in the regression itself, in the software, you can request that line, and the regression, the software, will give you the line. And but you'll have occasion to do that out in the world. Here, the idea is to see that you can do scatter plots, and then freehand draw them and get a sense of the direction, the strength, and whether there is a relationship. And then we come over to the next stage, which is the correlation. And here we can see it's the same thing, Florida crime rate, same sort of stuff at the top here. And now we've got the correlation table. And the correlation table, and you can look at the formulas in the book if you like, the correlation table tells us that the median income and the relationship to crime rate is 0.422. Now, if this was an inverse relationship, in other words, the line was going another way, this would be a minus 0.422. But since this is positive, we can see that it's positive, we would expect when we got to the correlation that too would be positive. And so there it is. It's positive, 0.422. Now, to get the coefficient of determination, we square 0.442, and that would be about 16, maybe 17, call it 17. And then we multiply that times 100, and we get the coefficient of determination of 17%, which then tells us this model, where we're using income to predict or explain the variation in crime rate, that it explains about 17% of the variation in crime rate. Now, you wonder, well, what happened to the other 83%? Well, that's the product or the subject of further research. It is the residual, what's left over, what is remaining once the model, you've gotten an idea of how much the model is explaining, then the residual is what is left over. Okay, so you would do one of these, interpret that, say it's positive or negative, square it for the coefficient of determination, write that out down here, and then multiply that times 100 and say, in this case, that about 17% of the variation in crime rate is explained by median income. That's what you do. And then we come to the regression table. Now this has a number of questions you haven't seen at this point, but it's basically the same thing. No hypothesis dependent and all of that. What is the total sum of squares, the total variation in the dependent table? Now you'll notice that there is an ANOVA table. So let's go over to this. Here, by the way, on our way, you'll see right here, I want you to do the math on the correlation. I want you to do the square of do this coefficient determination, describe what you see. But so you can check yourself, this value right here is that r squared. If you multiply the r and square it, this is the r in the correlation table, it comes to you again in the regression table. If you square it, this is what you will get. And don't just copy that, but do the math on this page and write out what you see. But anyway, we come down here, and this is an important table for us. If you can see, there's the word residual, which we talked about a minute ago, which is what is not explained by your model. The total here is the total amount of variation in the data. And I've done this. I did this morning. Where you've got something that looks like this, and there's the mean, and here's an x, and here's an x, and then the total variation. And then we got all these x's stacked up here. How much variation do we have? We got this one, this, and this, and between this, and 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 this. Every conceivable variation between any element in that distribution is summed up as the total sum. And there you can see it's 50,867 all of the this and this and this and this is this. All right? So that's the total. That's the denominator. And then we look at the regression model, and we see that's 90/70. If you were to divide 90/70 by 5867, you will get 0.178. That's how much of the total variation is explained by the variation in your regression model. All right? And then the residual, if you were to take 41,797 and divide that by 50,000, you would get the residual. If let's round this up to 18, that means that there's 82% that's unexplained. If you divided 41,000 by 50,000, you get about 82%. So the residual is what is left over that is unexplained. This is what is explained. This amount right here is the total amount of variation that you're explaining out of the total amount of variation. And this is how much of the total variation your model is not explaining. Okay, now, the other thing here, if we look at the significance, I want you to pay attention to the significance. It's 0.001. Now, I'm not asking you anything about alpha 05 or anything like that, but we know that alpha 05 is the standing alpha. And you look at that sig there, and it says 0.001. I would guess that you would say, if I were to ask you, is that larger or smaller than 0.05? You would say that it's smaller. So if it's smaller then, when you come over here, you can reject the null. And that there is, in fact, a relationship here. All right, let's move down to this table here, the coefficients table. And this is where we do some math. If I can erase this without tipping things over. Where we got a model that says y equals alpha plus beta times x, in the software, the alpha is the constant. It's this thing right here, the constant. And the reason it's called a constant, let me just put that up here, is if we, like here, let me use green. Here's the intercept. The intercept is crossing the y right here. So, ooh, that don't work too good. Let's try orange. So, orange comes across here. That's at the intercept. And they call it a constant because, in this case, this is how many hours on average a father does in household tasks before you begin considering the number of children in the household. So it's constant. It is the amount of, on average, that fathers do without regard to any other x, without putting any x in there. That's on average what it is. So they call it a constant. It's also the intercept because it's where it crosses the y-axis. Okay, so what we've got then, we've got y equals minus 11, 0.8, I'm just going to kind of round it up, plus, here is the beta, the big B, 2.636, 2.636, and times x. Now, what we do here, let me go back and say, this is the point estimate. I asked you about the point estimate. This value right here, that big B that you see here, that's the point estimate. Over here is the confidence interval for that point estimate. If we were to do a sample, 100 samples of the same size, go back to chapter 7, I think, and write, this is the point estimate. If we were to do 100 samples of the same size, the point estimate would vary between 1.1 and 4.0, 95 times out of 100. So you want to address that because I asked you to do it. That's why. And it's a good thing to know. It's always a good thing to do because we're in a sampling mode. We know that there's a variation out there if we were to do 100 samples of the same size. Is that not the case? Yes, we know that. Absolutely. So then we plug the things in where they belong, and then we do the math. So we go back over here to the first page where I say, referring to this. Now, I made a mistake here. So you can, I told the class this morning, you can write me up in red. It should say the dependent variable equals the intercept or the constant plus beta or the slope times x. So change that where it says equals the slope plus to the intercept or the constant, whichever you want to use. So here then, we do the math. If this asks you to do 8, I just put 18 in here instead of doing all the big numbers of 18,000. So we would do, let's see if I can do this here. I meant to do it first, but I didn't. So, and hopefully this thing will work. So then we do, I'm just going to round this to 2.6. 2.6 times 18 equals 46.8 equals plus 46.8, more or less. Y equals, then it's a minus 11.8. So then we take 46.8 minus 11.8, and that equals 35. So then we would say that at a median income of 18,000, we would expect 18,000, 350 per thousand, or 35 per 100,000, however you want to say it. But 35 deaths, or I mean, the crime rate would be 35 at 18. Now, if we were to do the next one, which is 40, and we put 40 here, then we would get something different. So then we do 40 times, I'll just do 2.6 equals 104, and then we subtract minus 11, we subtract 11.8 minus 11.8, and we get 92, if I did my math correctly. So there we can see that we were expecting, assuming this is the same scatter plot we were talking about. Well, here, the scatter plot we've been doing for this, we can see that the scatter plot is increasing as x's go up. So as median income goes up, we would expect a higher value of crime. Median income went from 18 to 40, and the crime rate went up from 40 to 92. So there you can see that we have predicted that at an income of 18,000, we could expect 40 per, a crime rate of 40, and at 40,000, we could a crime rate of 92, and that's an increase of from there to there. And we can, that's how an illustration from the demonstration how the regression works. Okay, so I think that's pretty much it. I've sent you the homework. It is similar. It's got a scatter plot, a correlation, and a regression, and a couple of values to plug in to do the basic math, to do the prediction. So that homework is due on Tuesday of after Thanksgiving. And next week we'll talk a little bit about what the final exam will look like. There will not be a exam 4. I was going to do an exam 4 for crosstabs and ANOVA, but let's not do it. I think we're doing all right with homework and everything. We don't need to take another exam. We'll let the exams at the final. There'll be an exam on this stuff that we're doing here, scatterplot correlation and regression. There'll be a one-part exam for that, and then an exam, kind of a final essay style exam. And we'll talk more about that next week. Okay, so that's all for now. And Thanksgiving break for the university starts in the morning. So we'll talk next week, and I hope you have a very nice Thanksgiving. Y'all take care, you hear?